All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. We're moving right along through Unit 6, Thermochemistry. We're in Section 6.3 now. And if you've been following along, this is covered Sections 5.1 and 5.3 in the text. So the last video we looked at energy diagrams, which was super fast because we looked at energy diagrams and kinetics. And so in topic 6.3, we're going to focus in on heat transfer in thermal equilibrium. All right. And so as we look at this, we're going to be looking at different forms of energy, how it can be transferred. And they're also going to talk about this state at which something reaches thermal equilibrium, where two objects at differing temperatures get to the same temperature so that heat is no longer being transferred between the two of them. That's going to be the focus of this video here today. So I hope you guys are ready to hang in there, to learn about it. Let's go. Let's get to it. So kinetic energy is where we're going to start because kinetic energy is important in terms of our temperature understanding. Now, kinetic energy by definition is the energy an object possesses by virtue of its motion. All right. And so essentially the energy of moving objects. Let's just call it like we see it, the energy of moving objects, right? We can calculate that energy by taking 1/2 the mass of the object in kilograms times its velocity squared. All right. And of course, we've got in this particular example, you've got the bicyclist in the first portion of the picture where the bicyclist is simply sitting at the top of the hill. She's got lots of potential energy, no kinetic energy. As she's going down the hill, her potential energy is decreasing and her kinetic energy is increasing, right? But kinetic energy, energy that an object possesses as it's moving, right? That's the big idea there. Now, there's also potential energy, all right? And I know you kids at Enloe, because you guys are a bunch of nerds. You know I love you when I say that, but you're a bunch of nerds. You walk around with your, I'm not lazy, I'm just brimming with potential energy. I've seen those t-shirts around here. Trust me, you guys have worn them. I know you have, right? But potential energy is essentially the energy an object possesses by virtue of either its position or its chemical composition. Right? And so essentially it's the energy that's been stored within this object, right? Now, at least in terms of it from a chemistry standpoint, certainly the chemical composition is important, but in terms of chemistry, the most important form of potential energy is actually electrostatic potential energy. And so that's E electric, and that's going to be equal to K times Q1 times Q2 over D. Now, K is a constant. Q1 and Q2 are the charges of the objects, and D is the distance that's separating those two objects, right? And so if you look at this diagram that's been represented here, if you have two like charges, their potential energy is going to be highest when they're closest together. So that would be kind of our scenario that's up at the top with the two blue spheres, Q1 and Q2. Their electric potential energy is going to be the highest when they're closest together, right? Because they're not actually going to want to be close to each other, all right? Whereas for oppositely charged particles, their electrostatic potential is going to be highest when they're farther apart from each other because they're going to want to try to get closer to each other, all right? So that's potential energy in a nutshell. Now, the conversion of energy is what's really important because we're going to be looking at this in our energy changes. We know that energy can be converted from one type to another. You got electrical can be converted to light. You've got chemical that can be converted into heat energy. Even in the example that we've seen thus far with the bicyclist, her potential energy is being converted into kinetic energy as she moves down the hill, right? So at the top, her potential energy is probably at its highest, assuming it's a pretty high hill. She's got all this energy stored up. As soon as she starts to make her way down the hill, her potential energy is going to be decreasing. It's going to be converted into that kinetic energy so that she can move her bicycle down the hill, move herself, and keep going, right? And so eventually, like if she gets to a bottom out point, that potential energy is going to be converted completely over to kinetic energy. And then the process can start over again, right? So there's this conversion of energy. Energy is always going to change forms, right? Can't be created or destroyed, but it can change forms. All right. Now this leads us into our idea of heat transfer, right? So heat transfer is what happens when warmer or hotter particles interact with colder particles, right? When they come in contact with each other, what happens is they collide, and as they're colliding, energy gets transferred between the two of them, right? And so as we're looking at this heat transfer, it's important to recognize that heat transfer follows a specific pattern, right? Or a specific process. Heat is always going to move from the hotter particle into the colder one. So that means that your hotter particles are always going to lose energy, and the colder particles are always going to be the ones that are gaining energy whenever they're in contact with each other. Okay. And again, that kind of summarizes that third bullet point. Heat is always, 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 always going to be transferred from our hotter substance to our colder substance. Now, something that's unique that can happen is that if those particles or if those substances can be allowed to be in contact long enough, what's going to happen is the two substances will eventually get to the same exact temperature, because the hot object is going to be continuously transferring energy into the colder one until they get to a point where they have the same exact temperature. Now, when they get to the same exact temperature, that's when that particular system or those substances are going to reach what we call thermal equilibrium, right? It means that in terms of energy transfer, there's going to be energy transfer that's taking place, but it's not going to be resulting in a change in temperature. The temperature is now constant because the energy being transferred between the two substances is no longer causing a change in the temperature. I hope that makes sense. All right. And our last thing, just to kind of put this into perspective, you've got the speed of the particles and then the probability that the particles can undergo some change that are taking place. So we've got water at temperature 1, temperature 2, and temperature 3. All right. And so the first question is, what can we say about the temperature of the water? At temperature 1. Well, looking at this graph, we can see that speed is on the x-axis. So for the farther we move to the right, the faster the particles are going to be moving within that particular sample of water. Now looking at sample 1, it seems like it's got the least amount of shift to the right. So what that's going to communicate to me is that temperature 1 is the coldest temperature of these three that are present. Okay. For number 2, what can we say about the average kinetic energy of water at temperature 1? Well, I think what we can communicate is that in comparison to temperatures 2 and 3, there's a much smaller range of kinetic energies that are experienced by the water at temperature 1. Because it's colder, that means the individual water particles are going to have a smaller range of values for their particles. In terms of the average speed, we can also say that the average speed for temperature 1 is the slowest. And then for number 4, 50 grams of water at T1 are mixed with 80 grams of water at T2. What can you say about the value of T final? Well, it's certainly going to be in between temperature 1 and temperature 2, but T final is going to be closer to T2, or maybe they're going to come to some value that's in between. But the thing that will happen is it'll take longer because you have more of the temp 2 water than you do the temp 1. So for number 4, they're going to get to some point that's in between. It doesn't matter that there's 50 and 80 grams respectively. All that's going to matter is that they're going to get to a thermal equilibrium, which is going to be somewhere in between the two. All right. And that, ladies and gentlemen, is everything that we need to talk about and discuss about thermal equilibrium and heat transfer. Hope this video was insightful. Please let me know if you have any questions. I'm always here to help you guys. Thank you so much for joining me, and I'll see you guys again soon. Take care.